This is a short introduction to how the fuel year cycle analysis differs from the year standard cycle analysis and how the actual cycle analysis differs from both the fuel year cycle analysis and year standard cycle analysis. So we had already discussed that the year standard cycle analysis, it makes a lot of assumptions, and that too very idealized kind of assumptions, wherein the working fluid is considered as an ideal gas. All the processes are assumed to be ideal processes, reversible processes, and the heat is assumed to be supplied from the source and to rejected to a sink, which is the reservoir, and there is no heat exchange between the system and the surrounding, and the working fluid has a constant value of Cp and Cv, which does not change with respect to temperature. So all these assumptions were made. Because of these assumptions, the values which we get are twice that of the actual values. So, for example, if you get a year standard efficiency of 54%, in reality, maybe you would be getting the actual engine efficiency as about 25 to 26%. Now, in order to reduce this difference between the predicted value and the actual value, we need to reduce the number of assumptions and make the analysis more realistic. Okay. So one way of doing it is to reduce the number of assumptions, and that analysis is called as the fuel year cycle analysis. Now in this analysis, that is a fuel year cycle analysis, we take into account many things which the year standard cycle analysis does not account for. So what are the things which we take into account which is not accounted for in the year standard cycle analysis? So the first thing is, we do consider here the actual composition of the cylinder gases. We know that in the year standard cycle analysis, we do not consider the actual composition of the cylinder gases. Here in the fuel year cycle analysis, we do consider the actual composition of the cylinder gases. Second point which is considered in the fuel year cycle analysis is the variation which the values of specific heat has when the temperature changes. So when the temperature changes, we know that the specific heat value also changes. But in the year standard analysis, we had not considered that change in the specific heat. In the fuel year analysis, we consider that there is a variation in the specific heats with the increase in the temperature, and accordingly we adjust our analysis. There is a phenomena which is called as a dissociation, which is just opposite that of the combustion phenomena. Combustion phenomena, you know that in the combustion phenomena, the products of combustion are formed and heat is rejected. There is an exothermic reaction. Now what happens is that when the heat is rejected during this exothermic reaction, the temperature also increases in the cylinder, and at those high temperatures, sometimes the products of combustion, they dissociate. Like the CO2 would dissociate to carbon monoxide and oxygen, the water vapor would dissociate back to hydrogen and oxygen, and when this dissociation happens, it is an endothermic reaction and energy is absorbed, and when the energy is absorbed, the power which is available during the expansion stroke, as predicted in the year standard cycle analysis, that is reduced. Okay, so this is the effect of dissociation which the fuel year cycle analysis does consider, okay, and which is neglected in the year standard analysis. Also, in the year standard analysis, we had considered that the number of molecules before and after heat addition remains the same, and that is because we had assumed that the heat is supplied not by any combustion phenomena but by bringing the source in temperature in contact with the working fluid. Here in the fuel year analysis, we consider that there is a change in the number of molecules before and after combustion. So this is the difference between the fuel year cycle analysis and the year standard cycle analysis. Then what are we assuming? Are we completely considering the actual cycle analysis in the fuel year cycle analysis? No. Actual cycle analysis is different from fuel year cycle analysis, because in the fuel year cycle analysis, we continue with certain assumptions. Okay, and what are those? The assumption is that we say that there is no heat loss during the expansion stroke and compression stroke. But in reality, in the actual engines, you know that there is a heat loss happening during the expansion and compression stroke. In the real engines, we consider friction. In the fuel air analysis, we do not consider friction. In the real engines, especially in the petrol engine, we are assuming that in the Otto cycle analysis, we are assuming that the phenomena of combustion, heat addition is instantaneous and it is at constant volume. In reality, the phenomena of combustion is not instantaneous. But in the fuel air analysis, as also in the air standard analysis, we assume that the burning is instantaneous. So we continue with this assumption in the fuel air analysis. Okay, and we also assume that there is a chemical equilibrium after combustion. So all these assumptions of the bed during the fuel air cycle analysis would deviate this cycle from the actual cycle, which we are going to discuss later. However, this cycle analysis, fuel air cycle analysis, actually does consider many of the actual things, not all, but many of the actual things, like the actual composition, the actual variation in the specific heat, the phenomena of dissociation, and the change in number of molecules. So this analysis, fuel air cycle analysis, gives us a better result than the air standard cycle analysis. In the actual cycle analysis, if you calculate the actual efficiency, we say that, and we see that the efficiency is much lower than the air standard efficiency, okay, and slightly lower than the fuel air cycle efficiency. Okay, the difference between the actual cycle efficiency and air standard efficiency is because of the fact that the actual cycle efficiency, as compared to the air standard efficiency, considers the variation in the specific heat, considers the phenomena of dissociation, consider that the combustion is not instantaneous, it is progressive, it takes some time. It also accounts for the incomplete combustion. It also considers the heat loss via the walls of the engine, and it also accounts for what are known as the blowdown losses. Blowdown losses means when you are opening the exhaust wall earlier, okay, some of the energy is lost. So that is called as a blowdown losses. So this is where the actual cycle differs from the air standard efficiency, and actual cycle efficiency is much lower, about 50% the air standard efficiency. Now, what things are considered, okay, in the actual cycle analysis, not in the fuel cycle analysis. So in the actual cycle analysis, we consider many things which actually, okay, happen in the engine. So actual cycle analysis is slightly more realistic than the fuel air cycle analysis. So as in the fuel air cycle analysis, we consider that the working fluid is a mixture, chemical composition changes, specific heat changes with respect to temperature, combustion takes time, heat is lost and gained from surroundings, there is a friction, there is some leakage also of the gas, and there is a blowdown losses. So you see that actual cycle analysis is a very realistic side of analysis. But why do we don't always go for actual cycle analysis? So because if you go on reducing the number of assumptions, as you have seen that air standard cycle analysis has maximum number of assumptions, fuel air cycle analysis, we have reduced the number of assumptions, we are moved closer to the reality. In the actual cycle analysis, we have removed all the assumptions and we are now considering the actual engines for analysis. But by reducing the number of assumptions, the simplistic analysis goes off and the analysis becomes a bit complex. Okay, so though we would get a very accurate result in the actual cycle analysis, but the analysis becomes complicated. Okay, so that is the disadvantage of actual cycle analysis. Okay, so this was the discussion on air standard cycle analysis, fuel air cycle analysis, and actual cycle analysis.